Okay, so we have exam 1 review today. Any questions about the exam before we start with some example problems? Okay, 1 page of notes, front and back, calculator, and pencil. Please remember to bring your calculator. Please remember to bring pencil. Yes? We'll do 1 o'clock. No, yeah, 1 o'clock. Right, because you guys have class at 2. So we'll do it by Zoom so that you can be wherever you need to be. Yeah.
You're going to record that?
Yeah, I'll record it. Yeah. It just sometimes takes a bit for Zoom to process and then upload and things like that. But I'll put it in the channel. Excuse me. Okay. So there is I don't know if I want to call it a study guide, but a list of objectives on Canvas of all of the topics. So I'm not going to cover all of the topics right now because you have a PDF of all of the concepts that we covered for the first exam listed on that sheet. Okay, but for the most part, it's going to be engineering basics. What are units? What do they mean? How do we convert between them? Things like hydrostatic head and pressure, temperature, things like that. Excuse me. Material balances. So this is going to be process flow diagrams, degrees of freedom. You don't necessarily need to do degrees of freedom, but it's a good concept to know so you know how to start the problems. Molecular and atom balances, stoichiometry, extent of reaction, multiple unit systems. So be familiar with what a reactor separator looks like. And then combustion reactions, right? So that covers, not a tremendous amount of concepts, but a lot of problems can be written that are varying degrees of difficulty. So those are the main things to cover. So I have an example here for hydrostatics. So in this problem, we're going to have 2 columns of fluid. This is going to be an oil. It is 2 meters high. Then we have a column of water. It is also 2 meters high. We have a pressure gauge at the interface, which is an absolute pressure gauge, and it reads 101.3 kilopascals. And we have a pressure gauge at the bottom that reads gauge pressure, but we don't know what it is. Pushing down the top, we have some pressure that is going to be open to the atmosphere. So the question is, what is the atmospheric pressure at the top, and what is the gauge pressure at the bottom? Yes?
Is this question from anything, or is this?
This is just a made-up question that I have, yeah. Just to highlight pressure differentials, hydrostatic head, and it also goes over units as well, because units are the biggest way that you can mess this up. So our hydrostatic pressure equation, pressure is going to equal P naught plus rho g h. So let's do a quick reminder of our units. My recommendation, always use SI. So density is going to be kilograms per cubic meter. Gravitational acceleration, meters per second squared. And height is in meters. So this gets us to, let's see, meters, kilograms, meters per second squared. And this should be equal to a Pascal. Now we can just double check that that's the case. A Pascal is a Newton per meter squared. A Newton is a kilogram meter per second squared. And I should get the right units. Hold on here. Units per meter squared. Oh, no, this is the wrong spot here. That's why. There we go. And that's kilograms per meter second squared. Yes?
Sorry, you might have said this and I just missed it. Where did you get the P equals P naught plus density GH?
This is the equation for hydrostatic pressure. So what this amounts to is this is the force acting on a column, right? So if I have, like, for example, my coffee, I use my coffee mug a lot for examples, right? It has a weight and it has a cross-sectional area, right? So the bottom of the coffee mug is pushing down on the table with a certain pressure. That cross-sectional area, if you do the math of the force per unit area, cancels out. So it only matters what the height of the column is. So that's how this equation is derived. Yes?
So is it only applicable for like cylindrical?
No, it's for everything.
Okay.
Yeah. Because it works out that and we use this also for the pressure, below the surface, for example. Right? So what's the pressure of oil in a well? You can do a first order approximation by this equation here using the average density of rock. I think it's like a PSI per foot as a rule of thumb for petroleum engineers. But yes, so the cross-sectional area cancels out, and that's how we get this. And that's how it just works out. But we didn't derive it in class. Okay, so when you're seeing hydrostatics, SI. Now, 101.3 kilopascals, this is not something I want to put in this equation. I want to put in 101.3 times 10 to the 3 pascals. Right, that's going to be a common error. So first, we can use this equation to figure out what the atmospheric pressure is, because we know the bottom of the oil column has a pressure of 101.3 kilopascals. So then we can solve for the pressure pushing down on the top of that oil column. Right, so the pressure here is 101.3 times 10 to the 3 pascals. This is equal to our unknown P naught plus, I forgot to tell you the specific gravity here. The specific gravity of the oil is 0.8. So that means 800 kilograms per cubic meter, or 0.8 kilograms per liter, or 0.8 grams per milliliter, right? So you can choose whichever units you want to have. All right, so then I just substitute this in. This is 800 kilograms per cubic meter. Gravitational acceleration, 9.8 meters per second squared. And the height is 2 meters. One equation, one unknown. Solve it however you'd like. This one's pretty straightforward to solve, so I wouldn't necessarily even use my calculator, even though I trust myself so little. In this case here, the P naught is equal to the atmospheric pressure, which is 85.6 kilopascals, right? So obviously the pressure on top of this column has to be lower than what we would consider standard atmospheric pressure, but this is not too dissimilar of what you would get at higher elevations. Right, so we're at less pressure by about, I guess, 2 meters of oil here. I think the pressure in Salt Lake is around 80 to 90 kilopascals, something like that. I don't remember. Okay. Now, next part is we want to know what is the pressure at the gauge here. So that's going to be the difference between atmospheric pressure and the absolute pressure here. So we could be clever about it and try and come up with a scheme, but I'm just going to solve for the absolute pressure at the bottom and then work it out. Right, so I know that the absolute pressure at the top of the water column is 101.3. So the pressure at the bottom of the water column is going to be 101.3 times 10 to the 3 pascals plus the information for water. So I'm going to truncate the units here. This is 1,000 times 9.8 times 2. And then we know the pressure at the bottom of the column is, where's my math here? 120.9 kilopascals. So then I take the difference between my 85 and 120. So I get that the delta P, or the gauge pressure, is 35.3 kilopascals. Now in my original example that I have in my notes, I have us convert this to different units. I personally like PSI just because that's what we use in the States, and so I kind of have an intuitive understanding about PSI. But I'll give you the units that are going to be the most common. So 1 atmosphere is equal to how many millimeters of mercury? 760 millimeters of mercury. Why do we use millimeters of mercury as a unit at all? It's traditional because mercury is super dense. So back in the days when we had to make barometers, right, a barometer is just a simple manometer. Take a tube, fill it with mercury, put your finger on it, flip it upside down. Actually, you probably don't want to put your finger on it because it probably weighs far too much for you to do that. And then what's the conversion for PSI? How much is 1 atmosphere in PSI? So what pressure do you fill your car tires to? Something like 30, 40, 50, depends on the tire, right? So how many atmospheres is that? All right, so one atmosphere is 14.7 psi. So this delta P here works out to be about 5.12 psi. So the pressure in your tires, if you fill it to about 30 psi, is about 2 atmospheres, which is the equivalent to about 20 meters of water height. Right, that's the force exerted if you were to dive 60 feet down underwater. Yes?
And then to pascals, it's 100 or 101.3?
101.3 kPa. There is one other unit conversion for pressure that you may see that's really common, and that is 1 bar is equal to 100 kilopascals, which is 10 to the 5 pascals. Those are some other common units for pressure. Yes?
If we need these conversions on the test, are they just going to give them?
Yeah, I'll give you the conversions you need. And a lot of times I'll just give you the I like to write the problems in units that are intuitive, but I don't necessarily want you to tinker with the units too much unless it's part of the problem. So if that's the case, I'll usually just give you the value in both units at the same time. One so you know, oh, that's intuitively what I understand, and the other one that's more easy to calculate. Was there a question? Yes.
So for like specific gravity, you gave us like 3 different units. You're like, oh, you can use this, this, or this. Are you going to give us units as well? Or
I'm only going to give you specific gravity. That's one I'd, yeah. So the specific gravity, right? One specific gravity is the same as the density of water. So that's 1,000 kilograms per cubic meter. Let me just write this out. So SG equals 1 equals 1,000 kilograms per cubic meter, 1 kilogram per liter, 1 gram per cubic centimeter, which is equal to 1 gram per milliliter. Now, if we were working predominantly in American engineering units, you would also know the conversion for pounds per gallon, but I don't know that one, or pounds per cubic feet. But I don't know those units. Right, but just burn this one into your brains. For the rest of your life, this is what density is going to be communicated in. Yes?
On your pressure one, shouldn't it be a 1 instead of 1,000 kilopascal or bar that by 1,000?
Which one here? This one here?
The 1,000 times 9.8 times 2.
1,000 times 9.8. I'm sorry, which part were we talking about?
Because that's in PA. Oh, never mind. I mixed it up. Sorry.
Okay, no problem. Okay. I'm going to erase this one just so I have a clean board. Okay, we good on this example? Covers units, hydrostatics, things like that.
I just have
Yes.
Sorry, just making sure I understand, because I didn't understand the chat. So we're trying to find P atmosphere and P gauge.
Yeah, so the atmosphere is the one pushing on the top, and then the gauge is the pressure at the bottom.
Okay.
The pressure what is the gauge pressure measurement of that pressure gauge on the bottom?
Okay, so and then that equals P naught plus density GH. That is the P gauge.
No, that's for the absolute pressure.
That's the absolute pressure.
Yeah, so for example, again, let's go back to my coffee mug here, right? The atmosphere is pushing on the top of the liquid, and I have some height of liquid, okay? So that adds additional pressure here. Now, if I wanted to know the pressure difference, I could subtract the atmospheric pressure from here and the atmospheric pressure from there. So I could take this equation and I could say that delta P is equal to the absolute pressure minus the pressure pushing on top if P naught equals the atmospheric. So in this particular problem, the top of the oil column is exposed to the atmosphere, so the atmosphere is pushing on it.
Okay.
But in the water case, it's not exposed directly to the atmosphere. It feels the atmosphere and the oil pressure pushing down on it.
Okay.
So in that case, if I'm looking at just the differential pressure, right, if P naught is atmospheric, then this is just equal to rho GH. So going back to my coffee, right, the absolute pressure at the bottom of my mug would be the pressure from the atmosphere plus the pressure of the column of coffee. So the absolute pressure would be atmospheric plus the hydrostatic. If it was the differential, it would just be the height of the liquid. Yes?
Could we also solve that by just finding the pressure exerted by the oil and then calculating the pressure exerted by the water and adding those two values?
Yes. So you could also combine this. So we could do the pressure at the bottom would be equal to P naught plus rho GH of the oil plus rho GH of the water. That'd be totally fine. Yes?
On the test, is there going to be any like manometer equations, or will it mostly be like this?
Could be manometer equations also. Okay. So let's go on to some material balances. So I have a non-reacting system and a reacting system material balance example. All right. So this is a stripping column. So being fed to the system, we have air with 5% mole of sulfur dioxide. The sulfur dioxide is being removed by having water, so stripping or adsorption, I think would both be appropriate terms for this. Having water being fed to the system. Right, so I'm drawing it like this because the air would go up, it would bubble through the water, and then the water would come down. So on the bottom we have water plus the sulfur dioxide. And this is where the thermodynamics comes into play. Now we don't have to worry about this right now, but in the real world we would have to figure out how much sulfur dioxide can water handle. And that's a thermodynamic equilibrium question. For this particular example, we're going to say there is 100 grams of sulfur dioxide per kilogram of water. Right? So let's say that's the solubility equilibrium limit. When we design a real process, we'll never go all the way to equilibrium. Otherwise, that takes an infinite amount of time. But let's say for the sake of purposes of this problem, this is how much sulfur dioxide can dissolve in the water. And then leaving the top of the column, we have our airstream. But because when you have dry air contacting with water, you're going to have some evaporating, this is going to have 3% water. So the question is, if 100 kilomoles per second fed to the process, how much water do we need? Right, so we're having 100 kilomoles per second fed. Yes?
Is that percentage, mole percentage
Mole percent.
on the H2O as well?
For everything, yes. Mole percent for everything. This is in mass percent, so we're going to have to tinker with this just a little bit. Okay, so we're going to feed sort of dirty air with sulfur dioxide in it. We're going to use clean water to remove the sulfur dioxide. Some of that water is going to be evaporating into the airstream. Right, so not super obvious where we begin. I would say the water balance is probably the one we don't want to do because water is not here, but water is here, here, and here. Right, so we have an unknown, unknown, unknown flow rate. Air, we have 1, 2. That one's pretty easy. Sulfur dioxide, we have 1, 2. So it seems like we want to start off with either SO2 or air. Water is the one we have to save for after we have the whole thing balanced. Okay? So first we have to deal with this. So everything else is in moles so far. This is in a mass ratio. So let's play with this a little bit here. So we want to know what is, and I'm going to label my streams here, stream 1, stream 2, stream 3, and stream 4. So what we want to know is what is Y of SO2 for stream 3. That'll make our life a lot easier because then we can just do mole balances. So we have 100 grams of SO2 per 1,000 grams of water. We can use the molecular weights here to convert this. So we're choosing a basis of 1,000 grams of water here, and then we're doing the calculation. So that gives us, so for every 1 mole of sulfur dioxide, it is 64.1 grams. And again, if you have a unit conversion like this, I will give you the necessary conversion. But I trust that your chemistry teachers effectively taught you how to calculate molecular weights. Right? And then for water, we have 18 grams of water is equal to 1 mole of water. And this results in 0.028 moles of SO2 per mole of H2O. Right? Grams cancels with grams, grams cancels with grams, moles per mole. So now I have a mole ratio.
Is that supposed to be per 1 mole of H2O?
Yes, so this is how many moles of sulfur dioxide per mole of water. Not quite.
Just like in your notation, 1 mole.
Oh, sorry, I said H2. There we go, H2O. Sorry, my bad. Yeah. Okay. So this is not yet the mole fraction, right? But again, we can use the same concepts of material balances to solve a lot of problems. We can choose a basis, right? So I'll choose a basis of 1 mole of water. So that means that the mole fraction of sulfur dioxide for 1 mole of water is going to be 0.028 moles of SO2 divided by the total number of moles. Well, I chose 1 mole of water plus 0.028 moles of SO2. Right, so this concept of choosing a basis and doing a material balance, you don't have to always have a process flow chart that requires that you do that. Right? You can just proactively use this in a lot of different other applications. So choosing a basis and then performing your calculations around it makes life a lot easier. And we get that the mole fraction is almost the same, 0.0273 moles of SO2 per mole. So not per mole of water, just per mole. That's the mole fraction. So we got the mole fraction now. So now we can actually start doing our material balances. Good so far? So let's knock out the sulfur dioxide balance. Okay, so this is a non-reacting system, right? So then mass and moles can be interchanged. They're only different by the molecular weight. So it's just in equals out, right? This is an open steady state process. I can't be losing any mass. So in equals out. So that tells me that I have 5 kilomoles of SO2 per second coming in, right? Because that's 5% of 100, right? So pretty easy calculation there. And then leaving the system, I have an unknown N3 flow rate multiplied by the mole fraction, 0.0273 moles of SO2 per mole. Okay? So I'm being diligent with my units right now, but in a second I'm just going to flip off and stop putting the units down. So we have time to actually get through the rest of the problem. And then we can just solve this equation. One equation, one unknown, 0 degrees of freedom, 183.15 kilomoles per second, right? So that's N3. So sulfur balance, sulfur dioxide balance, check. Let's do the air. That one's the next easiest. 1 in, 1 out. Okay. Okay, so air balance, we have 95 coming in. Is this moles per second, kilomoles per second? It doesn't really matter, right? But we know that we've chosen a basis of 100 kilomoles per second. So I'm just going to write the 95. And then this is going to be then equal to where do I have it here? Oh, this is just equal to n dot to air. All right, so that one's pretty easy. Alternatively, we could have also written that this is equal to 0.97 times n dot 2. So that gives us a flow rate of stream 2, which is 97.9 kilomoles per second.
Sorry, where's that coming from?
Because we have 95 kilomoles per second of the air coming into the system. So if it's 5% sulfur dioxide, that's 95% air. So that gives us, from our basis, 95 kilomoles per second of air coming in. The total flow rate of stream 2 has a total composition of 97% air. The 3% is water. So I take the total flow rate of stream 2, multiply it by the mole fraction of air, 0.97, and that gives me the total flow rate of stream 2.
But you also set 95 equal to N2.
This is n.2 air.
Okay.
So this is the species flow rate of air in stream 2.
So it's 95%, right? Wait.
So the feed is 95% air. The outlet is 97% air. And that this is, Jay, a question here.
Yeah, I was just wondering, kind of in general for your questions, do you have, like, you don't put the units to go fast? Are we expected to put units on every number? Because I know we're also.
It's a risk-reward strategy. So
you're not going to punish them, but it
No.
might burn us if we get units wrong.
if everything's a disaster, then it could hurt you. But if you're on the right track, don't worry about it too much, right? Because this is painstaking, right? I'm going painstakingly slow through these problems. The hope would be is that this one here you could knock out in less than 10 minutes, right? So 5 to 10 minutes is what you should aim for on a problem like this. Now the challenge that you're not getting access to right here that will be necessary on the exam is I'm not going to draw the process flow chart. I'm going to describe the process. So I tried to describe how I would communicate it in the written form, sort of as I was walking us through the problem. So for this one here, I would say, I would have to give you a little piece of information because you're not all expert chemical engineers, right? A stripping column does this job, right? So you know what the process does. Then I would say you have air fed with this % of whatever, okay? This compound is being removed by a water stream. The water stream leaves with this amount of composition, and then the air leaves with this amount of composition. And I would say that there's, you know, things like I would clarify, hey, is there air in this stream here? I'd say no, right? That's a question you could ask in class, right? Otherwise, the descriptions will all be like a paragraph long. So I'll keep it simple. So unless I explicitly state that there's in there, right? So for example, on the practice exam, I said that like the slurry stream has some organic in it, right? That's to let you know that there is some organic, but you don't know what it is, right? And if it's you know, and if you know that like, you know, air is probably not going to dissolve in the water, you can suss out some of those details. But those are questions I'm totally willing to answer in class. Yes.
So you're saying you'll specifically say what's in a stream?
I will generally try and make it what I think is clear. But what I think is clear and what you think is clear may be two different scenarios. So always ask a question. I'm happy to walk through that.
Sorry, one more question. This next exam is also going to be 6 questions, right? Or is it going to be 5?
Likely. If it's 5 questions, the questions will be a little bit harder.
Okay.
But again, don't feel bad. I'm not expecting people to get 100. Not expecting people to get 100. But I want people to have the opportunity to shine. But the final exam will be much more accommodating and more easy to get 100 on.
Will there be test corrections?
Test corrections, what do you mean by that?
Like, we can get it back and like,
Yes, so there's a regrade policy, right? So,
like where we can correct it and then we get like.
oh. No, I don't have that system yet. Yeah. Okay, so let's finish up this example problem here. So for the water balance is the last one. Now, so something like this, like in your exam strategy, it would be very helpful if you could write out water balance, right? Because that doesn't take that long, right? Because the time it took for me to write kilomoles of SO2 per second, I could have just at least outlined what it was. But I can suss out, because I'll be looking at 60 of these exams, right? I'll know the numbers, right? So if you can just tell me which balance you're doing, that'll really help, and it'll save you some time knocking out the units. I would not recommend you skimp on the nomenclature of your unknowns, right? But I'm okay like if you drop the mole fractions there. Like that's pretty easy to suss out what it is. Like if you say SO2 balance N3 times by a number, I'm like, oh, that's the mole fraction, right? That's pretty clear to me. So that's a strategy that I'd recommend. All right, so the water balance. Coming into the system, we only have one water feed, and that's N4. Leaving the system, we have our airstream N2 that has 3% water, plus leaving the system, we have stream 3, and that has a composition of 1 minus 0.0273. Right? So we've already solved for this, we've already solved for this, and we can get the necessary flow rate of water, which is 181.1 kilomoles of water per second, right? So having like the units at the beginning and the end and like a description of what balance you're doing, that should be plenty enough. And honestly, if I'm working out my own solutions to help drive the problem, solve the problems, like when I'm writing the homework, I won't do the units, but I will tell myself this is this balance, this is this balance, things like that. Yes?
Also, what tolerance do you give for the answers?
I'm generous.
Okay.
Like if you truncate a couple of numbers, that's not going to be the end of the world. Like you don't have to get it to 7 digits of precision. But sometimes if it's like really far off, then it's kind of hard. But if your work is super logical to follow and you're off by like 1% because of rounding errors, that's not a big problem. That doesn't bother me. Okay, last example is a reaction example. Got about 15 minutes, so let's try and hammer through this one. Okay, so in this one we have benzene plus hydrogen forming cyclohexane. And we're going to do this in a reactor separator. Now, this is a simplified reactor separator. Where I don't have a splitting stream. Okay, so the pieces of information that we get are 20% single pass conversion. Okay, what does that mean? 20% single pass conversion. Yes?
In a single pass, 20% is converted to that.
Yes. So we have material being fed. It is mixed with the recycle stream. Whatever's fed to the reactor, 20% of it reacts. Okay, then you have a separator that sends it back. So this is a little bit simplified because normally we have a purge stream here that wastes some material.
So is that first box a mixer?
There's the mixer, reactor, separator, and then normally we'd also have a purge stream, but for this example, I simplified it a little bit. We don't have the purge stream.
So is it safe to assume on the exam there will be a purge?
Not necessarily. The reactor separators you've seen have mostly had all had purge streams. Okay, so then we have 95% overall conversion. Right, so the overall conversion, right, ultimately when we do an overall balance, we don't care what's going on the inside. We just look at the in and the out. So the overall process gives us 95% conversion. The single pass gives us the conversion just of that material flowing through the system. We have 20% excess hydrogen. And we have that the recycle stream is 22.7% benzene, which means that 77.3% hydrogen. So I have this is benzene, this is obviously hydrogen, and then this is cyclohexane. Okay? So that's how we would have this described. Yes?
Is that mole percent?
Yes, everything's in mole percent. Okay, so I kind of walked us through. Cyclohexane is being synthesized by having benzene mixed with hydrogen in a reactor separator process. There is no purge stream in this cycle. That's what I would write in the statement. The single pass conversion is 20%. Single pass conversion of benzene is 20%. 95% overall conversion. The process is fed with 20% excess hydrogen, and the recycle stream has this composition. That's exactly what I would have written in the exam statement. Right? So you would have to know what is the reactor separator, because I'm not going to draw the process flow chart. Okay. The question is, what is the recycle ratio? Oh, my chalk is getting small. Okay, that's the question we're going to answer in this problem. Okay, and a new chalk. Okay, so none of this information is flow rate dependent, so that means we get to choose our own basis. I'm going to choose a basis of 100 moles per second, for example. Just make it a nice round number. Okay, so what I would say is let's first close this up. So this is 100 moles per second of benzene, right, to make it easy. So 100 benzene. So what should the flow rate of hydrogen be? Now, you may or may not be provided this balanced reaction. You may need to balance the reaction yourself. So what's the flow rate of hydrogen? Yes? With 20% excess.
300 plus 300 times 0.2.
So that'd be 360 hydrogen. You can do this in your head or you can write it out, but tick off the easy things first. Now you're like, okay, so how do I figure out the recycle ratio? So I'm just going to fill this in here, 22.7 benzene and 77.3 hydrogen. I'm going to label my streams 1, 2, 3, 4, and 5. So we could spend a lot of time just thinking around and looking at this, but why don't we just take some of the design specifications and apply them right away, the ones that are really, really straightforward. So which is the easiest design specification that we can apply right away, you think?
Overall.
Overall conversion. We have one stream in, one stream out. So 0.95 is the overall conversion. That's in minus out over in. So that's going to be 100 minus N5 benzene over 100. And that tells us that the outlet N5 of benzene is equal to 5 moles per second. Okay? So we
Is that 4 or 5?
sorry, 4. My bad. N dot 4. Okay, the flow rate of benzene in stream 4 is equal to 5. Yes?
Is the outstream going to be pure C6H12 or will it contain any benzene or hydrogen?
We don't know. So we can list these unknowns right here. So we have N for benzene, N for hydrogen, N for cyclohexane. But based on the composition of stream 5, we know that there's no cyclohexane recycling back through the process. This is actually a bad example because the benzene cyclohexane separation is actually extremely difficult. So forget about that. Fantasy problem with the chemistry world. Okay, so now that I've got something linked from my inlet to the outlet, I can balance now the remaining two components here, right? Because it's one chemical reaction. So these compositions are all linked together through this reaction. What strategy would you like to employ to solve this one?
Mole balance.
Mole balance?
I feel like atom balance.
Atom balance, I think, would really suck on this problem.
Yeah, that's what I was saying.
Because you got to have like one benzene. For every one benzene, you have 6 carbons. Hydrogen, you have 12, right? Okay, molecule balance is probably really easy to do. You can knock that one out. I would recommend extended reaction on this one, right?
Oh, right, 20%. Done.
Well, so for single pass conversion, we'll have to do that. We're gonna throw in a little mole balance in here as well. But I'm going to use an overall extent of reaction. Okay, so the number of moles of benzene, right? And I'm just going to do this overall. I'm not going to. I'll do this. N for benzene, right, is going to be equal to what we fed to the system, which is 100. And then what is the extent of reaction for benzene in the system here?
95.
Sorry. What's the stoichiometric coefficient, I mean? -1. So minus the extent of reaction. Okay? So we know from our overall conversion that this is 5. So that means that our extent of reaction has to equal to 95 moles per second. Right? So I added an extra unknown. By gosh, it's really a nice unknown to have, right? It makes our life a lot simpler. So then we can just knock out what are the flow rates for stream 4 for the hydrogen. So hydrogen being fed to the process is 360. What's the stoichiometric coefficient of hydrogen? So it's -3. So it's -3 times the extent of reaction. So that means that the flow rate of hydrogen leaving the system would be 75 moles of hydrogen per second. Okay? And then for cyclohexane, N for cyclohexane, right, what do we feed to this system? 0. What's the stoichiometric coefficient for cyclohexane? 1, so it's plus the extent of reaction, and that tells us that we have 95 moles of cyclohexane per second leaving the process. Okay? So we've checked this off, we've checked this off, we've checked this off. Now this is where we get a little bit of trickery coming into the system here. We can do a cyclohexane balance on the separator. Okay, so I have cyclohexane leaving in stream 4. None of it is leaving in stream 5. So that means all of the cyclohexane in stream 4 is in stream 3. Right? We did this in our heads, but that's a cyclohexane balance on the separator. So that tells us that N3 cyclohexane is 95 moles of cyclohexane per second. Okay. What do we think is the next design specification that we should do? Let's do a balance. Let's do a benzene balance or a hydrogen balance on the separator. Well, we don't know what the total flow rate of stream 5 is, so that's one unknown. We don't know what the total flow rate of stream 3 is, that's another unknown, so I can't really apply that. So what's the last remaining design specification we could work out? 20% single pass conversion. So now we're actually going to toss in a secret molecule balance. Okay? So 0.20, right? So this is the benzene conversion, is going to be equal to N, so it's in minus out, in minus out over in. This is also going to be to moles reacted over moles fed, right? So I'm feeding a certain number of moles of benzene, right, and I'm reacting a certain amount. But the problem is we don't know how much benzene we're feeding to the system because we don't know what our free cycle is, and we actually don't necessarily know what our flow rate is because we don't know how much is being separated in stream 5 also. So what we can do is we can toss in a molecule balance, okay? So for every 1 mole of cyclohexane formed, that equals 1 mole of benzene reacted. Right? So this is the concept. This is what we do for the molecule balance. Rate of formation of one is rate of consumption of the other. In this case, for every 1 benzene, we get 1 cyclohexane. Right? So we're doing a little bit of extent, a little bit of molecule balance. We didn't do an atom balance, but I think that one's pretty straightforward. Okay. So that tells us then that we get 0.2 is equal to 95 moles of benzene reacted over our feed rate of N benzene in stream 2. So that tells us that the flow rate of benzene in stream 2 is equal to 475 moles of benzene per second. Okay, so we're getting close. We've only got 2 more calculations and we are completed with this example. All right. So everyone's got like another exam coming up or something, I guess, huh? Okay, so I'll do it really quick then. So the benzene balance on mixer. This one is 100 fed to the system plus 0.227 from the recycle stream is equal to 475. This tells us the flow rate of stream 5 is 1652, and the recycle ratio is equal to 1652 divided by how much is fed to the system, which is the 100 benzene plus the 360 hydrogen, and that gives us a recycle ratio of 3.59. Right? So if I send this benzene through the process several times, I can take a 20% single pass conversion and make it into a 95% final product. So that's the power of the reactor separator.
So how do you end up with a recycle ratio is greater than 1? What does that just mean?
That means that this pipe is a lot bigger than this pipe. Right? So you're flowing a small amount in, but the process equipment here just gets bigger. Right? So this is now an engineering decision for financial points, which is how much recycle do you want to do to get your conversion higher? Let's say the benzene's really cheap, and you just say, hell with it, I'll just burn the product that I don't use to make energy, right? Because if you want to get this to 100%, then this stuff has to be infinitely sized. So there's going to be some cutoff of conversion that is going to be your ideal amount. And that is what the whole senior year is focused on, is how do you make that decision? It's not easy. Because you have to basically build the whole unit in a computer and then use heuristics to figure out if the reactor has to operate at this temperature and this pressure with this volume, this is how much it's going to cost to buy, this is how much it's going to cost to maintain, this is the cost of buying the benzene, this is the cost of selling the benzene at this composition, at this composition, at this composition, which is the most profitable plant you can build. Right? Because when you go and buy chemicals, you can buy HPLC grade, reagent grade, cleaning grade, right? And all of those, the more pure it is, the more expensive it gets. So how pure do you want to make it? How much do you want to sell it for? All right. Question?
So the recycle ratio is moles of 5 over
Yes.
1.
N5 over N1. And in this case, there's no splitter. So if there's a splitter, you would have this purge stream here. Now, the purpose of the splitter is to remove inerts, right? So a really classic example of that is ammonia synthesis. Right? It takes the takes the nitrogen from the air, but there's other chemicals that are there. So if I'm sending in a little bit of material here, and let's say I'm separating out only the liquid products, like ammonia can be condensed to a liquid pretty easily. Hydrogen and nitrogen, not so much. So I'm going to be sending all of my hydrogen, right, and nitrogen back, but any impurities in the system is going to cause accumulation of it. And eventually, you'll have a lot of argon and a lot of CO2 in the system and not a lot of hydrogen and things like that. So that's what the purge stream is for. So you can't get 100% conversion if you have any impurities or side reactions. And that largely depends on the quality of your separation. But for something like the Haber process, right, ammonia can be pretty easily condensed out. Hydrogen cannot be condensed out. Okay. Yes? For the purposes of the exam, I'm usually keeping that somewhat limited, but in the real world, yes, there will definitely be that. But that makes the problem pretty tedious to solve. So I make sure that the problems are tractable to solve in a reasonable amount of time. Question?
Was there like more examples that we didn't get to because of time?
No, you're good, yeah. These are the ones that I had planned out. Because it covers the main topics. Non-reacting balances, engineering, and reacting balances and multiple processes, right? But the concept of multiple processes is just sort of like a puzzle that you have to solve, right? Which one do you want to start with? Rule of thumb, if you can do the overall balance, do the overall balance, because that's just like one process. Who cares about all the mumbo jumbo that's going on inside of here, right? Do the overall balance. That's the easiest one to start off with. Then march your way in from the front or in from the back. Very rarely will you have some design specification right in the middle and you grow out from there. Right? It's usually front to back. Start off with the overall and eat your way in. See y'all Friday.